So good evening, everyone. Uh, in this tutorial, we will be talking mostly will be solving problems related to your nuclear physics problems. Okay, so I can wait for a couple of minutes if anybody wants to join. Okay, then I will start. Okay, so let's start today's tutorial sessions. Okay, so in this class, what we will be talking mostly about your basic problems. So good evening, everyone. Okay. Yeah, so in this tutorial, okay, according to your assignments, okay, it's mostly related to uh, basic problems on nuclear physics. Okay, so what I can suggest is regarding the books which I follow is this is the concept of modern physics. Okay, it's chapter 11 which deals about nuclear structures, and this is a basic like a very beautiful books, okay, which has many informations about it. Okay, so if you want to refer, this is one of the for basic understanding, this is one of the most common textbooks. Okay, so according to the problems which is already there in the assignments, it's mostly related to your binding energy. Okay, how do we calculate binding energy of your reactions? So if I want to just give you a little idea, if you look at this, um, if you look at any elements, okay, usually represented by x, a, z. Okay, I can write it here on the sides, x, a, z. Let me just write it here. Okay, so what is A? A is the mass number, X is the elemental, representation, and Z is the atomic number. Okay, so this is what you have already known about these things when you say that the atomic number is in fact the number of the protons in the nucleus. Okay, nucleus contain both protons and neutrons, and collectively you can call protons and neutrons as the nucleus. Okay, so if I want to represent, okay, so let me write this as week 11. Okay, if I want to express your elemental representations, usually represent as x, a, z. Okay, so where a is what? Where a is the mass number, and z is your atomic number. Okay, when I say atomic number, means it is your number of protons in a nucleus. Okay, so if I have to find out what is the number of neutrons, because in nucleus there are both protons and neutrons, you use the relation a is equal to um, n plus z. So your mass number is the total number of protons and neutrons. So your number of neutrons is equal to a minus of z. Okay, so that will give you the number of and then neutrons also. So fine. So but what we are more interested is your binding energy. Okay, this is one of the beautiful concepts of binding energy, is actually the amount of energy required to hold the protons and neutrons together, or what is the amount of energy required to break out the protons and neutrons. Okay, so that is what you mean by binding energy. But the higher the binding energy means the more stable is your elements. Okay, so if you go back to this concept of modern textbooks, okay, it's already, yeah, so this is what I was talking to you, that there is uh, x, a, z. You represented your elements by x, a, z. And if you look at the binding energy which is already given to you, uh, let me just check it out. It is in the chapters. Yeah. So the definition, according to test textbook, the definition of a binding energy is very simple: the missing energy that keeps a nucleus together. Okay, or what is the amount of energy required to keep the nucleus together. Okay, so that is what it is called as a binding energy. Okay, so when I say binding energy, I usually, how do we calculate? This is very, very important. How do we calculate the binding energy? Okay, so example, it is given to you here, like a hydrogen isotope deuterium, which is equal to 2H1. Okay, has a neutron as well as a proton, right? Why am I saying has a neutron and a proton? Because here Z is equal to 1, right? So the number of proton is equal to 1, whereas A minus of Z, which is the number of neutron, which is equal to 2 minus 1 is also equal to 1, which is the number of neutron, right? So this is the number of proton and this is the number of the neutron. Okay, so we will expect that, like when you add one hydrogen plus one of neutron, you should expect the mass to be the same. Correct, because you are adding one proton and one neutron to form this one H2. Okay, ideally you will expect that the mass remain the same. That means the sum of the masses of the reactants is equal to the masses of the products. Okay, that we will expect. But actually it is not. Okay, there is a missing mass, and that mass, if we convert it into the energy, that mass, if you use the Einstein relation, del E is equal to mc square, you get what is called as your binding energy. Del E is equal to mc square. So this del E is actually equal to mc square, or del mc square, whatever is called as a mass defect into c square, you will get the energy. And this energy, okay, so it's also represented, 1U is equal to 931.49 MeV. We will use this also formula, that 1U is also equal to 931.49 in terms of energy. Okay, in terms of energy, it's equal to 931.49 MeV. Okay, so in these problems, mostly in your assignment problems, I will start solving now. So mostly it deals with binding energy. So you can understand that binding energy is that in fact recalculated it if there is any mass defect, first of all. Okay, so or it's what is the amount of energy required to remove one protons or neutrons. You will see what is the binding energy. Okay, so other than that, yeah, so ideally the definition of a binding energy is in fact this one. So what do we get? The binding energy in milli electron volt. Okay, it means we have converted any mass in terms of energy, having this chemical composition X, A, Z. As I have told you, A represent the mass number, total number of protons and neutrons, whereas Z represent the number of protons, and N, which is the number of neutrons, is given by what? Z, the atomic number into the mass of the proton, plus N, the number of neutrons into the mass of the neutrons, minus the final mass of the proton, into 91.49 mc square. So how do you get this relation? This relation is very easy. It means that, okay, let me write it here. Your binding energy, delta, I can write binding energy is equal to Z, mass of the proton. Okay, that is the total number of protons into the mass of the proton, plus the number of neutrons into the mass of the neutron, that you will get the reactants. Okay, that means proton and neutron react together, minus your the mass of your final products. Okay, and this one, if you convert into energy, multiply with 91.49 MeV, you get the binding energy. Okay, because the mass is usually represented in terms of atomic mass, and if you convert into of energy, 1U is almost equal to 931.49 MeV. So whatever the mass, if you convert it, if you multiply with 91.49 MeV, you will get the energy. Okay, so let's calculate what is the first problem. Okay, in your assignment, that will be more clear maybe. And what it says is calculate the energy release. Calculate the energy release or absorb in a reaction where 3 alpha particles, remember this point, 3 alpha particle, He24. Okay, this is an alpha particle. Okay, it's also is the same as a helium-24 combined to form carbon. which is carbon 12. Okay, so if you look at it, that means this is like a reaction in which if you add three alpha particles, you get a carbon. Okay, that is a question. So in doing so, what is the amount of energy, whether the energy will get released or the energy will get processed? That is during the reaction. Okay, so if I want to write these reactions, ideally I will write, let's say, the nuclear reactions can be represented as what? You have 3 He2 4, because there are 3 alpha particles, you get carbon 6 12 plus some energy plus some Q. Okay, Q can be greater or equal to, can be greater than 0 or less than 0. Okay, if Q is less than, if Q if Q is greater than 0, that means energy is released during the process. Okay, if Q is less than 0, then energy is absorbed. Okay, and this Q is called as a Q value of the reaction. So now if we have to find out whether the energy is released or absorbed, what do we have to use? We have to calculate what is, we'll use the concept of your binding energy, that we have to find out what is the mass of the initial products and what is the mass of the initial reactants. Sorry, what is the mass of the initial reactants and what is the mass of the products, and then we will see whether how much is the how much is the mass defect. Okay, how much is the change of the mass, and finally we will convert that into the energy. Okay, so so mass, I think it is not given in your questions, but I can give you the mass of the helium-24. Okay, you can cross check, is approximately 4.002603 U. Okay, this is a unit of mass, and the mass of your carbon 612 is approximately equal to 12.0 U. Okay, so now if you look at it, okay, what happened? You can calculate what is the mass defect. So the mass defect, because if you want to calculate energy, first you need to know what is the mass defect. So the mass defect, you can also write as delta M. Okay, is the difference between the total mass of the reactants and the mass of the products. Okay, and the mass of the products. So this is the same thing like we saw in the binding energy from the concept of modern physics, this equation. This is the same thing, except that here we have multiplied with 931 MeV by U. That is why you get the energy term. Otherwise, if you include only this mass term, you call it as a mass defect. Okay, the first term here is called as a mass defect, and if you multiply with 91.49, you get the energy. So that is called as a binding energy. So same thing here, when I say the mass defect is actually the difference between the mass of the reactants and the final mass of the product. It's simple. Okay, so now the del M will be equal to what? 3 into the mass of 3 into the mass of your helium-24, 3 of them, minus the mass of your 612. Okay, so what happens is you will get 3 into, you substitute this 4.002, which is the mass for, I think this might be confusing, let me just write a little, not x, it might be confusing with your elements, so let me just write small x. This multiplication for 0.002603, okay, minus the mass of the carbon is given is 12.0 U. Okay, here is also the unit is U. Okay, remember is U. Now if you multiply and then subtract this one, you will get a mass difference of 0.007809, which is very small. Okay, that is a small mass difference in it. This is called as a mass defect. And these difference of mass, if you use Einstein, which is equal to E is equal to mc square, that means 1 U Okay, 1U, that means the U that you can do the conversion. Okay, there, I don't need to do the conversion here, but you can find out there's a conversion of 1U in terms of mass. You can convert in terms of energy. 1U is equal to 931.49 MeV per c square. Okay, so that means your energy E equal to delta mc square, correct? Delta mc square from your equation, let's say from equation 1, this is your equation 2. So substituting equation 1 in equation 2, what you will get is at 0.007809 into what? Since this is unit U, correct? This is unit U. So you convert unit U into 91.45 MeV. Okay, that is what you can do. So you can convert this 1U, which is obtained from your mass defects, into 931.49 MeV per c square, into c square in way is there from your energy, del E is equal to mc square. So c square and c square will get cancelled, and this energy comes to around 7.27 MeV, or I would rather say here Q value. Okay, now what happens is that using this relation, I mean from here you get the Q value to be positive. So when Q value is positive, or if del M is greater than 0, that means Q automatically is positive. You get energy is released. Okay, so this is your first questions of your assignments. I think there is also question number B, which says that, yeah. Okay, so I hope you understand the first problems. Okay, and the first problems, what do we do is that it's simple. We just take the mass difference, okay, can convert in terms of energy. So whatever the mass difference that is there, if you convert into the energy and find out whether it's positive or negative, you will get what is your quality factor. Okay, quality factor is in fact related to the energy released or absorbed in a nuclear reaction. Okay, so this is a pretty simple problems. Now the question number B, I think it is in the same questions, question 1 set B, which says that determine the binding energy of the last proton in the carbon-12 nucleus. So just like determine the binding energy of the last proton in, remember this is a proton in a carbon-12 nucleus. So you have a carbon-12 nucleus and you have to find out what is the binding energy of the last proton. Given, okay, it's also given to you, mass is already given to you to be equal to mass of carbon-12 is equal to 12.00052 AMU, atomic mass unit. Then B11 equal to 11.01006, and the mass of the proton MP equal to 1.00759 AMU. Okay, so this question also is exactly the same. Okay, there is no difference between these questions and the questions A, except that the reaction is different. That's it. Okay, so what does it say? It says that what is the amount of what is the binding energy, or determine the value of the binding energy when there is a reaction of carbon to boron, right? So this is B11 and mass of the proton. So if I write this reaction, what will happen? You get carbon-12 will goes to B11 plus what? You see, this is mass number 12 and this is mass number 11, and plus mass of the proton. Sorry, plus 1 proton. Okay, it has to be conserved. That means here that is 12, here is 11 plus 1 equal to 12. This is not minus 1, this is 1. Okay. Now, before you solve any problems, you have to write the reaction, and the reaction has to be conserved. Here you have mass number 12, so B has mass number 11 plus 1 proton. You will have 12 mass number. Okay, so this is very, very important. Now the same thing. Now you know what is the reaction. You know what is the reaction, and you have to find out what is the binding energy. We do the same thing. First of all, we have to find out what is the mass defect. Okay, what is the difference of the mass? So here, what happens in mass defects? mass defect delta M will be equal to, okay, this is your mass boron plus mass of the proton, okay, minus mass of the carbon, because this is your final products, correct? So if you add boron 11 plus 1 proton, you get what is a carbon 12, right? So now if you do this, your mass defects delta M equal to what? Equal to, then you substitute what is the mass, MB, MP. Okay, I will write here, maybe I'll write MC here, MB here, clear, and MP. Okay, so you can substitute what is the value of MB, what is the value of MP, and what is the mass of the carbon, and you will get in this way. So I can just substitute here 11.01006 plus 1.00959. This in unit is in U, or atomic mass unit, minus 12.00052 U. Okay, you will get a mass difference of 0.01713 U. You can cross check this calculation. Okay, you can cross check this addition and subtraction. Okay, so now once we get the mass difference, we can easily calculate in terms of energy, which is equal to, binding energy is equal to delta M C square. And this is in terms of U, you can convert in terms of energy as what? 1 U is equal to 931.7 for your proton MeV volt per C square, 1 U. Okay, if you go back, if I can just quickly share it to you, I think there is another conversion here, energy, which is already given you in the table. Somewhere, energy conversion, just a second. Yeah. So you see here, there's already an energy conversion to, if you want to have a look and understand it. You see proton, neutron, electron, one hydrogen atom. Okay, so what happens is that these proton, neutron, electron has a slightly different mass. Okay, slightly different mass. This is 1.6726, this is 1.6726, and 1.675, that's 0, right? So if you are talking about the proton, then you might have to use 938 and 939 and so on. Okay, so now what we will do now is that we will use the same concept here of 931.7 approximately. Okay, approximately 931.7, and you will get something like delta M, you already know, and C square you can get something like 15.956 MeV. Okay, correct? Or 91, I can use the same energy, or 91.49. They are not that much difference. Okay, so you can use 1 U, you can use the conversion of 1 atomic mass unit into MeV by C square. So I have used 91 approximate, but if you want, you can go back to this your calculation and substitute accordingly, whether it's a proton or a neutron. So in this case, we are talking about a proton, so you have to use 1 U for a proton. But they are not that big difference, because anyway, if you look at the energy, they are very, very small. They are very, very closely related to one another, 98, 939, 938, and so on. Okay, so I hope you understand about this problem. Okay, fine. Now there is a question number 2, which is also very, very closely related to your binding energy. So the question number 1 is pretty straightforward. You calculate what is the mass difference, and you should substitute the energy conversion. That's it. You can convert it into energy. Okay, there is no nothing confusion about that problems. Okay, and the question number 2 is given that consider the binding energy is given to be AVA minus of A as A to the power 2 by 3 minus of A symmetry 2z minus of A whole square by A minus of AC z square by A to the power 1 by 3. Okay, so what problem is this? Okay, this is a very a very standard equations which is called as semi-empirical mass formula. Semi-empirical mass formula. Okay, in all the textbook you will see that the binding energy is expressed in this form. Okay, so the first question is provide an explanation of each terms. Okay, so what I will do is that I will just tell you, okay, what is the first term, second term, third term, third. The explanation you can write it. There are a lot in the there are even in this concept of modern physics. Okay, if you read, they are explained that the what is your first term, second term, third term, and fourth term. Okay, that means binding energy. In fact, initially it was supposed to be binding energy AVA. What is AVA? This is called as a volume term. Volume term, what does it mean? It means that your binding energy is proportional to the mass number. Okay, that the first term is called as a volume term. That means if suppose if A is more, then the binding energy also should be more. Okay, but there are also nucleons on the surface of the nucleus, and which does not interact the same as the nucleus inside. I mean, as the nucleons inside. Suppose if you have a nucleus, there are nucleons at the center, and also there are nucleons on the surface. So these nucleons and the nucleons on the surface, they interact differently, because nucleons here, they are surrounded by all the nucleons, but for the nucleons on the surface, it will be surrounded only on one side. Correct. There are no nucleons on the other side. So in other words, you can see that the interaction will be different. Okay. So that is why, or in other words, I would rather say the nucleons at the center have more neighbor nucleons, whereas the nucleons on the like on the surface has less neighboring nucleons. Okay. In other words, I would rather say that. Okay. In that case, this asymmetry comes because you have to subtract the binding, otherwise you are overestimated. Okay, so the as term, the as, this reflects what is as a surface term. Okay, so the proper explanation that you can write it by yourself. Okay, that you can check in many nuclear physics books. They explain in detail that why this volume term, why this surface term. Okay, so the answer for this question is you have to just explain what is the first term, which is the volume term. You also have to explain what is a surface terms, as, and also you also have what is called as a base as, called the asymmetry. Asymmetry based on the number of neutrons and protons inside the nucleus. Okay, whether it's odd or whether it is even. Okay, that is how the binding energy also will get modified. And finally, you also have what is known as a Coulomb energy. Okay, so what is a Coulomb? The Coulomb energy represents the electrostatic repulsion between your the nucleons. Okay, so this is called as a Coulomb term. Okay, so the first term is called as a volume term, that is AVA is called as a volume, sorry. The AVA represents the volume term, ASA represents the surface term, A asymmetry, the third term, represents the asymmetry term. Okay, and finally AC represents the Coulomb term. Okay, so the first part of the question is for you just to write what does this terms means. Okay, so that I'll leave it to you to write a few sentences about what is a volume term, what is a surface term, what is a asymmetry term, and what is a Coulomb term. Okay, so fine. Now your question number B is determine the most stable isomer, okay, for A equal to 216. Okay, so just give me a minute, please. Just give me a minute. Yeah, so the question is determine the most stable isomer for A equal to 216. Okay, I hope you still remember what is isobars. Isobars mean same mass number but different atomic number. Okay, same mass number but different atomic number. Okay, that is isobars. So what the question is that the binding energy is already given to you. Okay, you have to find out what is the most stable isomer, that is the most stable elements for A equal to 216. You have to find out. Okay, so because elements can exist in many forms. Could be your A is the same, A is equal to 216, but your Z will be, let's say, let me just give you an example. Let's say a equal to 216, but your z could be some any value z1, or could be z2, or could be z3. Okay, that is what. Or what I can write is, a x z1 comma a x z2, where a remain the same but z value remain is different. Okay, that is the value of z are different. So in order to find out which of these elements are the most stable, what you need to do is that you can differentiate that your given equation with respect to z. Okay, because z we have to find out, right, what is the most stable isobars for the value of z. So that is what you have to differentiate the binding energy by dz equal to 0. Okay, you find the stability equation dB by dz equal to 0. This is called as a stability equation. Now if you differentiate this one, dB by dz, that means you differentiate this equation 1, let me name it this equation 1, with respect to z. So the first term and second term there is no z term, so it will goes to 0. Only third and fourth term there is a variable z, so you have to differentiate it with respect to that. So if I write it, I can write in this with d by dz of, let's say, AVA minus of a as symmetry a to the power 2 by 3 minus of a as symmetry 2z minus of a whole square by a minus of a c by a to the power 1 by 3 z square. Okay, if I am not wrong, I think in your assignment again there is some mistakes. Okay, I think the fourth term is written as positive here. Okay, the fourth term is written as positive, but in fact it is not correct. It should be negative. Okay, I think you can correct it. Now if you differentiate this one, this will be equal to 0, this will be equal to 0, since there is no variable on z. So there are, what you need to differentiate, you have to differentiate only the third and the fourth term. So if you differentiate, you will get minus of a as symmetry, okay, minus of a as symmetry, or d by dz of binding energy equal to what? Is equal to minus of a as symmetry a 2z minus of a into 2 minus of twice of a coulomb z divided by a to the power 1 by 3. Okay, here I have just differentiated this equation with respect to z. Okay, and then what you can do is that you can again solve this for a as symmetry to z minus of a divided by a minus of 2acz divided by a to the power 1 divided by 3. Okay, so this is your d by dz of binding energy. So if I equate this to equal to 0, this term to equal to 0, to find out the stability of z, then this equation will be equal to 0. So what I can write is that I can substitute maybe 1 on the right hand side. I can write 4 as symmetry 2z minus of a divided by a equal to minus of 2acz divided by a to the power 1 by 3. Now it's very easy, because now there's only term what? There's only term of z a only. So you can rearrange this equation in terms of z. So you can write twice as symmetry to z minus of a divided by a equal to minus of acz divided by a to the power 1 by 3, and rearrange it again with z. You get z equal to twice a as symmetry a divided by 4 as symmetry constant plus ac a to the power 1 divided by 3. Okay, I forgot to mention you that this a asymmetry, small a and small ac, they are constant term for asymmetry term and for the Coulomb term. Okay, they are the constant values, and usually it is given to you when it's given to you in the question. So I'll just write it here. So usually it is given to you, a is equal to 216 according to the question is already given to you. A asymmetry is equal to approximately 24 millielectron volt, and AC is equal to 0.75 millielectron volt. Usually this is given to you, or any textbook will provide this constant and the value. Okay, so once you get that, you substitute back a, you know, asymmetry, you know, like constant asymmetry, constant for a Coulomb term also, your z comes to around 224 into 216. Anyway, the millielectron volt and the millielectron volt will get cancelled, because there is also a numerator and a denominator, so you don't need to worry about it. So you get 4 into 24 plus 0.75 into 36. And if you solve this equation, you get approximately 84. So then this comes to the conclusion that your element A, Z, the one which is the most stable is 216x84. Okay, this is your most stable element out of many possible elements that you can have that with different Z values. 84 is the most stable values. Okay, so this, okay, so I think you understand now what is the what is this binding energy. So in this tutorial, mostly we are the first question and the second question we have talked only the binding energy. Okay, we have talked only the binding energy and what is the most and the stable isobars. To determine the most stable isobar, what you need to find out, we can just differentiate your binding energy with respect to Z and then you equate it to 0. Okay, so I hope you understand that these two problems. Okay, next, the third problems also is pretty more or less the same. Okay, it's pretty more or less the same. Okay, I can solve it. Okay, okay, so in question number 3, yes, again it's the same, using the semi empirical formula, which of the following, which of the nuclei He24 or beryllium-4 6 or lithium-3 6 is the most stable? Okay, so this is what you have to find out. Okay, which of these elements is the most stable? Okay, that is the same question as last time, but last questions. Okay, but in the last question, it's asked which is the most stable isobar. Here it is asked, okay, what is the most stable elements or most stable nuclei? So what you need to find out? Semi-empirical formula is, it's already given. Okay, and just a second, is it given or just a second? Yeah. Okay, so let me just a second. 3. Okay, fine. So what we will do is that we will write the same formula, whatever we have done in the second questions, we'll write the same thing. So that means your binding energy, I can write on the binding energy A comma Z is equal to what? A volume term that we have already known, minus of surface term, your Coulomb energy term, your asymmetry term. I can write only let me just say AA. I can write AA first, square divided by A, plus there is also another term called parity term. Okay, parity term depends upon the even numbers of A of proton and number of neutrons. Okay, otherwise this is what we have seen in the previous. There's also a parity term whether it's a positive or negative. Okay, I will show you that the values of this parity term. Okay, so fine. Now if you if you find out from any textbook, AA is approximately equal to 15.75 millielectron volt, AS is approximately 17.8 millielectron volt, AC Coulomb energy term is approximately 0.711 millielectron volt, and A asymmetry equal to 23.7 millielectron volt. Okay, and finally parity term, delta of A comma Z, your parity term is approximately equal to AP, which is equal to A to the power minus of half, which depends upon A to the power minus of half if even Z even N. Suppose if the number of both the number of neutrons and both the number of protons are even, then your parity terms depends upon your A to the power minus half, otherwise equal to 0 for odd number of mass number, and minus of AP A to the power of half, minus of half for odd atomic number and odd number of neutrons. So if both protons and neutrons are even, you have this relation AP a to the power minus a to the power minus 1 by 2. If both are odd, then you have minus of AP a to the power minus of half. So you just need to add these values in the above term. Okay, now again what happens that AP, let me just, AP is approximately also 11.18 millielectron volt. Okay, so all the constant terms are provided. Okay, you just need to substitute and put the value of A. That's it, A and B, and find out what is of all the three elements, which has the most binding energy or which has the highest binding energy. The one which has the highest binding energy will be the most stable. Okay, that we have already seen. The higher the binding energy, the more stable is your elements. Okay, so here also is the same thing. You just need to substitute what is the value of AV, what is the value of AS in your equation. Let me name this as an equation 1, and then calculate what is your binding energy. So let me just show you the first point, He24. This is your first nuclei that you have to find out. Okay, so for this you have A equal to 4, correct? Z equal to number of proton is equal to 2, and what is the number of neutron? Equal to A minus of Z, which is also equal to 2. So if you look at it, you have even proton, even number of neutron, and for that you have to use this equation for the parity, AP a to the power minus of half, with AP also provided to you. Now let's see the volume term first. The volume term, it will be equal to AVA, right? 15.75 into A. A is what? A is already given to you, 4, which is equal to 63.0 MeV. Correct? The surface term will be equal to 17.8 into A to the power 2 by 3, which is equal to what? 17.8 into A is what? 4 to the power 2 by 3, which is equal to approximately 44.85 electron volt. Okay, so you just need to substitute in the equation, in this equation. What is AVA, what is let me just write them, what is AVA, what is asymmetry, and you already know what is Z, what is A, what is the constant, and you just need to put all the values. Okay, so let me just quickly write what is the Coulomb term. So the Coulomb term will be equal to 0.711 into, let's say, 2 into 1 by 4 to the power 1 by 3, okay, equal to 0.896 millielectron volt. The asymmetry equal to what? Equal to, let's say, 23.7. Since they are both the same, you will have something like 4. If you look at it, what happens? If you look at it, we can get something A minus of 2Z. So A is 4 minus 2 into, if you look at this equation for your asymmetry, if you look at this equation, what happens? A is 4 and 2 into Z is equal to 2, you will get 0. Automatically you will get 0. So you get 4 minus 4 divided by 4, which is automatically 0. Pairing energy, you have 11.18 into A to the power minus half, since it is an even, which is equal to 5.59 MeV. So once you know all these values, you can just substitute here. Binding energy of He24 equal to what? Equal to 63.0 minus of 44.852, 0.896 minus 0 plus 5.59. So if you find it out, you will get something like 22.842 MeV. Okay, so this is the energy, but remember that this is the total energy. Okay, in order for you to find out which is the most stable nuclei, you have to find out binding energy per nucleon. Okay, you have to divide it by the mass number, which is the total number of nucleons in a nuclei. Okay, divided by A, you will get binding energy per nucleon. This will tell you the higher of this value, the higher will be the stable will be your nuclei. Okay, so binding per nucleon, you just take 22.842 divided by 4, which is approximately equal to 5.71 MeV per nucleon. Okay, so for a hydrogen atom, for a sorry, not for hydrogen, for a helium, now the He24, now we get a binding energy per nucleon of 5.71 MeV per nucleon. Now we can do we can do the same thing again. We can do the same thing again for the second nuclide. The second nuclide is what? The second nuclide is beryllium 6. Sorry, not this way. 6 4. What happens in this case? A equal to 6, which is the mass number, Z equal to 4, and finally N will be equal to 6 minus 4 is equal to 2. Okay, here is also even event. So what you need to do is that again you have to find out that what is your volume term. Substitute A, substitute Z, and substitute N. Instead of like 2 to 2 in the above case, you can substitute 6 for 2, right? And you can get something like binding energy for beryllium. I will not solve it, but it's the same thing. Is equal to 94.5 minus 58.77 minus 4.695 minus of 15.3 plus 4.564. So you can cross check these numbers. Okay, you can cross check these numbers. 9.7 MeV. So if you divide it per nucleons, binding energy of beryllium per nucleons, that is per A, equal to 3.29 MeV per nucleon. So if you look at these two elements, what is the first thing that you see? The first thing that you see is for a nuclei, for a helium He24, you have 5.71, but for Be64 you have 3.29. So automatically you can say that your He24 is more stable than your Be46. But there is another one nuclei which you have to find out, lithium, according to your question. So lithium 3,6. This is also given to you. So in this case, what is happening? Just give me a second, please. Yeah, so for your lithium 3,6, what is A? A equal to 6, Z equal to 3, and N equal to 3. Again, what you need to do? A is 6, Z equal to 3, N is equal to 3. And remember this one. Remember this. Z is 3, that means odd, and N is odd. So what you have to find out? You have to use this formula. Minus of AP. For odd Z and odd N, you have to use this one. Minus of AP, A to permissive. Not this one. Not positive AP, it will have to be minus of AP. So if you look at it, if you just substitute what is the value of what is the value of A, what is the value of Z, and what is the value of N, you can conclude to be something like 6 equal to 94.5 minus 58.774 minus 2.348 minus 0 minus of 4.564. Okay, so these values corresponds to 28.814 millielectron volt. Okay, so if I have to divide it by per nucleon divided by A, this comes to around 4.8023 MeV per nucleon. So if you compare the binding energy per nucleon of the three nuclei of your lithium, beryllium, and helium, you will see that your helium has the most binding energy. That is corresponds to around 5.3, right? Corresponds to 5.71. 5.71, then comes 3.29, then comes 4.8. So if I have to, we can conclude from here that your binding energy per nucleon of your helium 4.2 will be greater than your lithium 6, and finally will be also greater than the beryllium 6.4. Because why? The binding energy of your beryllium is higher than of your lithium is higher than your beryllium. So if you look at these three elements, which is the most stable nuclei, you can say that the most stable nuclei is helium 2.4 because it has the highest binding energy per nucleon. Okay, so I hope you understand that this problem is the same thing and what we have done in the last two problems also. So fine. So all the first problem, second problems, and third problems, more or less they use the same. I mean, we use the same formula for the binding energy. For either we calculate the binding energy, or we find out what is the most stable isoburst, or we find out what is the most stable nuclei. Okay, all of these that are the same. Okay, are using the same formula. Okay, using the same formula, which is the binding energy formula. Now there is another questions, your question number 5. This is might be slightly little different. Your questions number 5 from your assignment, it talks about radioactive elements or radioactive sample. So like radioactive samples are those samples, in which they are unstable, and which they keep on in which they keep on disintegrating. Okay, and they keep on disintegrating till they reach the most stable nuclei. Okay, so that is what this radioactive is, or what does radioactive means. It means that you have an unstable elements, and then it keeps on disintegrating to reach to the most stable state. Okay, so that is what you know about uranium and so on. Okay, why it's highly risky, because it keeps on emitting radiation. It keeps on emitting radiation till it reach the most stable elements. Okay, so that is the different sections in which what is the most stable elements that the uranium will likely not the end up to. Okay, it will keep on disintegrating. Fine. So so from here, I think you remember. Let me before solving this one, I think you still remember the law of radioactive decay. So what is the law of radioactive decay? Says that the number of nuclei at a time t, okay, the number of nuclei remaining at a time t is given by n equal to n naught e to the power minus of lambda t, where n naught is the number of nuclei at a time t is equal to 0, and with time, how does the number of nuclei remaining? It scales the exponentially. So if I draw the graph, it will be something like this. This is your n naught, this is your time t. So the number of nuclei that are remaining decays exponentially. Okay, so here lambda is called as a disintegration constant. Okay, so so what is the radioactive decay law? Says that you know the value of n, the number of the atoms nuclei at a time t remaining is equal to n naught, which is the number of nuclei at time t equal to 0 e to the power minus of lambda t, where lambda is the disintegration constant and t is the time. Okay, so the problems. Okay, the question number 5 says that a radioactive sample has a half-life of 60 days. Okay, so half-life, I think you know half-life is usually half of the time in which, is the time in which half of the radio the samples are decaying. Okay, so that is 60 days. And question number 8, determine the disintegration constant. And the average lifetime. And the average lifetime of the sample. So there are two terms here that you need to find out. First is your disintegration constant lambda, and one is your average time t. So there is a, you can look at it. There is a derivation where do you where you can get the relation between your t half, that is your half life, your n, your lambda, and so on. Okay, and from the main equation itself, you can substitute here t is equal to t half, then n will be equal to n naught divided by 2, then you will get the relation something like ln is equal lambda is equal to ln of 2 by t half. This is a simple problems in which if you substitute in this main equation 1 t to be equal to t half, then n you also substitute to be n naught divided by 2, okay, then you will get a relation like something lambda, relation between your disintegration constant and your T half. Why do you need a disintegration and T half? Because the problem is given in terms of your half-life. So you have to relate what is the disintegration constant and your and the half-life. Okay, so finally you get ln of 2 is very simple. Okay, ln of 2, you know what is the ln of 2, and T half is given to be 60 days. This is pretty straightforward, 0.011 per days. So this is the disintegration constant. Nothing is equal to 0.011 per days. Now, question number B. Question number B, it says that calculate the average lifetime. So average lifetime is given by, let's say tau is given by, is inversely proportional to lambda. So lambda is equal to what? Lambda is equal to ln of 2 by 2 half. So 1 by lambda will be simply equal to T half by ln of 2. Okay, I use the same formula. Now T half, 60 days divided by 0.693, because ln of 2 is equal to 0.693, and this equation to be 86.56 days. Okay, this is a very simple problem in which once you know the formula n is equal to n naught e to the power minus of lambda t, in which how does the atomic nuclei decay, that you can easily calculate what is your half-life and what is your the average life as well. Okay, so just give me 2 minutes, please. Okay, I'll come back in 2 minutes. Yeah, okay, so sorry for that. Yeah. Okay, so in these problems, okay, what did we find out? We find out that for knowing the disintegration formula, okay, or the law of radioactive decay, how does the elements decay using the equation n is equal to n naught e to the power minus of lambda t. Okay, you can easily calculate what is the half-life and what is also the average life. Okay, not only the half-life, you can also calculate what is the disintegration constant and so on. Okay, so the question number B from there, the set B says that calculate the time required for 2/3 of the ordinal atoms to disintegrate. Okay, this is also very important. Calculate the time required for 2/3, that means exactly 2/3 of the original atoms to disintegrate. So that means we have to find out how long that does the elements disintegrate 2/3 of the original atom. Suppose if the original atoms is n naught, how much is your time in which 2/3 of n naught that will be disintegrated. So we use the same formulas like the nt is equal to n naught e to the power minus of lambda t, which whatever I have given to you. But here we have to find out what is nt, because you have to find time. Okay, and lambda you already know, right? Lambda you already know. So from the above equations or from the above calculation, now you have to find out nt. So what is the number of remaining atoms? Initially is n naught, and minus how much you have, how much you want to find out, 2/3 of n naught, right? This is 2/3 of n naught will get disintegrated, right? So now what happens, you get 1/3 n naught. So the number of atoms remaining is simply 1/3 n naught equal to n naught e to the power minus of lambda t. Use that equation here. Okay, so how do we get this equation? This is nt is the number of atoms remaining, so it will be equal to n naught initial minus which we want to find out. Okay, how much is that? 2/3 n naught. Okay, 2 by 3 n naught is a disintegrated elements and n naught is a initial element. So the number of atoms or the number of the nuclei, let us say the number of nuclei is 1 by 3 n naught. Okay, fine. Now n naught and n naught term will get cancelled. So we get 1 by 3 equal to e to the power minus of lambda t. Correct. So you can take to be something like log of on both sides. Ln of 1 by 3 is equal to minus of lambda t, because log and exponential will get cancelled one another. So you get lambda t is equal to simply ln of 3. If you multiply negative sign on both, then you can simply convert ln of 1 by 3 into simply ln of negative 3. Now what is the time? Now time is equal to ln of 3 divided by lambda. And how do you get lambda? Lambda is can be calculated from here is 0.01 0.011. So it will be equal to ln of 3 divided by 0.011 per days, right? So the time will be equal to 95.09 days. Okay, so I hope you understand this this problems. Okay, it's pretty straightforward. It's a formula based problems in which you can just substitute in the main equation and then solve what is the final value. Okay, so I have one more questions to solve, then maybe I can stop for 2 days. Okay, any more questions we can always talk, you can always mail me. Okay, that is always. And if you want to solve more problems, we can always solve during the supplementary classes. I think there are 2 classes supplementary. Okay, fine. So there is one more problem which I think I will solve. That is a question number 4. Okay, and then after that we will close the 2-day sessions. So yeah, so let me just write the question. So question number 4 from your assignment. This is slightly different, okay, compared to the first and the third questions, and then the first 3 and the 5th questions. Is determine the minimum energy required by a photon to produce an electron positron pair in a process electron plus gamma. You have electron plus positron plus electron. So this is a very interesting problems in which you have to suppose there's a reaction of electron plus a photon, and you have to find out what is the energy required for a gamma such that it will produce these 2 things. Okay, so that is the question. Determine the minimum energy required for your gamma such that you will be able to produce the electron plus the positron. Okay, E plus and E minus. We represent the electron with E minus and the positron with E plus. Fine. So here, if you want to find out, we can use your conservation of energy and momentum. Okay, that is the most standard. We can see it as a standard way to find out what is the minimum the energy. So if you want to find out the conservation of energy, what happens? This initially is addressed, correct? So you have E I. Okay, so this is address. So and this is, let's say it has an energy, let's say E gamma. I would rather say this is E gamma. So let me just write it a little more. So let's say a photon with energy E gamma, and let's say momentum P gamma equal to E gamma by C, okay, hits a stationary electron of mass m, right? So this is at rest or stationary. So you have a photon of energy E gamma, let's say, and a momentum E gamma by C, because E is equal to Pc, so P momentum is equal to E gamma by C with a stationary electron of mass m. Now what happens? Your total energy EI, what will happen? You will get E gamma, which is the energy of your photon, plus your rest mass energy of your electron, mc square. I think this, you know, this is the total energy. That's the equation 1. Now your initial momentum will be simply what? E gamma by c, right? Because your electron is at rest. So you have your initial, you have your initial and the energy and momentum. So now, if you want to find out what is the minimum energy, we can use, you can use the invariant mass, invariant mass, okay, and using this concept, okay, let me just write it on the side. E square is equal to p square c square plus m naught square c to the power 4, and this and this we have seen in your quantum mechanics. E square is equal to p square c square plus m square to the power 4, so we get or we can write E is also equal to mc square, so we get m square c to the power 4 equal to so sorry, not this way, I can write this way. You can write here m square c to the power 4 equal to E square minus of p square c square, and you can write m square c square will be something like E square by c square minus of p square, right? Because c square and c square, and they will get cancelled on the right hand side. Now you can use this the formula here and try to find out what is the initial condition. So for the initial condition, what happens? I can represent by S, which is equal to mc square, which is equal to what? Energy. Energy is initial energy is EI square by c square, okay, minus initial momentum pi square. Okay, so EI square initial energy is E gamma plus mc square. So E gamma plus mc square whole square, and also divided by c square. Correct. And initial momentum also will be simply E gamma by c whole square. So then we solve this equation, we can get something like E gamma square plus twice E gamma of the photon mc square plus m square c to the power 4 minus of E gamma square divided by c square. And finally we get 2E, because E gamma and E gamma will get cancelled, 2E gamma, and c square and c square also will get cancelled, so you can get something that's simply m plus m square c square. Okay, so this is your initial state. Okay, if you use this concept, this is equal to m square c square, you will get this is your initial state. Okay, this is your Erston. Now what happens after the reaction? Okay, so that is what it is asked. Okay, determine the minimum amount of energy. That means you have to find out what is E gamma. That is what it is asked. So now for the final state, what happens? In your final state, your three particles, now you have three particles, right? Your three particles, your electron, your positron, electron, move at each other, okay, and the total mass will be simply 3m, because each of them has a mass m, and then thus you can write S is equal to m square c square, which is equal to 3m whole square c square, which is equal to 9m square c square. So if you want to find out the minimum energy, we can just equate, let's say, equation 3 and equation 4, both are the same. Then you can write 2, let's say, from 3 and 4, 2E gamma m plus m square c square is equal to 9m square c square. So if you find out, you get E gamma equal to 4mc square, right? So for the rest mass of the electron, now you know that this is mc square, right? Mc square is actually what? Is actually for electron is 0.5 MeV. I think that you still remember. It's already there in their concept of modern physics. I think here somewhere, yeah, this one, electron is equal to 0.5 MeV. So then if you substitute, you get E gamma equal to 4 into 0.5 is approximately equal to 2.0 MeV. Okay, so for what is the minimum amount of energy? The minimum amount of energy for a photon to generate electron and positron is approximately 2 millielectron volt. Okay, in this case. Fine. Now the second set, which is the last questions, is what is the energy? Let me just check. a nucleus with a mass number of 220 decays of mass number of 220 decays to the ground state of a daughter nuclei, releasing a disintegration energy Q value, determine the energy of the emitted alpha particle. Okay, so that is what it is asked. So this is rather say it is releasing what? It is releasing a daughter nucleus. So you have a nucleus with a mass number of 240 and it decays to the ground state, and also decays with a daughter nucleus and also a Q factor of 5.26 MeV. So you have to define what is the energy of the alpha particle. So that means when you say alpha particle, it automatically represents this an alpha decay, right? An alpha decay, that means you have A comma Z initially. What happens? You get A minus 4 now comma Z minus 2. That means the daughter nuclei will have 4 less mass number and 2 less atomic number. Okay, so here also we have to use a similar category and plus here plus He24. Okay, so that makes sense. A comma Z is equal to A minus 4 Z minus 2 plus the alpha particle. Okay, He24. Now the Q value is in fact is the kinetic energy. I can rather say it's a kinetic energy shared by daughter nucleus and the alpha particle. So Q value is also given to you, which is also the kinetic energy of the daughter nucleus as well as your alpha particle. Now we use conservation of momentum. Okay, so what is the conservation of momentum? Assuming that your parent nucleus is addressed. So remember that is a parent nucleus, I can write as P, and you also have a daughter nucleus plus alpha particle. Okay, in simple words, you have a parent nucleus, it disintegrates into a daughter nucleus and plus the He24. Okay, now assuming that your parent nucleus is addressed, so what will happen? Your magnitude of your daughter nucleus will be the magnitude of your alpha particle. Conservation of momentum, because why? Because your parent nucleus is addressed, so you have momentum equal to 0. Then the conservation of momentum says that your daughter nucleus should be equal to your alpha particle. Now also you can also use an approximate non-relativistic approximation. Your kinetic energy is equal to P square by 2m, correct? So Q is equal to K alpha plus K of the daughter nucleus, which will be equal to P square alpha by 2m alpha plus P square of your daughter nuclei divided by 2 mass of your daughter nucleus. This will be equal to what? This will be equal to kinetic energy alpha 1 plus m alpha divided by m d. This is Q. Okay, so this is how you so how do we get this? We can just take common P alpha by 2 alpha, so you will get what is your kinetic energy of the alpha particle. Now since A is already given to you, A is equal to 240 from your question is already given to you, A is equal to 240, then m alpha of the alpha particle is almost equal to 4u that we have already seen from the first problems, and mass of the daughter nuclei md will be equal to 240 minus of 4 is approximately 236 u. Okay, then you can just substitute K alpha equal to Q divided by, just substitute back in this equation. K alpha is equal to, you can write this as equation star. So from equation star, K alpha is equal to 1 plus 4 divided by 236. Q is already given to you. Q which is equal to 236 divided by 240. And Q is already given to you from the question, is called 5.26 MeV into this 236 divided by 240, which is approximately equal to 5.17 milliton volt. Okay, so yeah, so these problems is a slightly little different problem, but compared to the first three and the fifth questions. But here the question is, you have to find out what is the minimum energy of your, the first question is what is the minimum energy of your photon such that you can generate positron and electron. Whereas the second case, suppose if you have a nucleus and it disintegrate into a daughter nucleus plus alpha particle. So how do you calculate what is the energy of your alpha particle? Okay, so the kinetic energy of the alpha particle or the outgoing particle. Okay, so that you can use the conservation of momentum as well as the conservation of the energy. Okay, so I think all the problems I have solved for this tutorial sessions. Okay, so maybe I can stop here. If you have any questions, feel free to ask me or feel free to mail me also. We can always solve some more problems. If you find that you need more problems to solve, yeah, you can always mail. We can solve during the supplementary sessions. Okay, so I think for today we will stop here. Thank you very much for attending the classes. I'll see you next week.